guys, we're gonna walk through this quiz a little bit just to hear the key. I sent the PDF along with this video, but I wanted to give you guys a chance to look at it as well. It's nice to talk through it sometimes, so I'm gonna go. Let's go full screen here so you guys can see this a little bit better. Maybe I can get it to go here. Here we go. All right, I'm gonna walk through this bit by bit. Number one, the question was find all three the function and f prime of x, f double prime of x. And I put those up here, so if you're looking for f prime and f double prime of x, they're up here at the top. Those are the derivatives. Do one derivative followed by the second derivative. And then it says evaluate each of these. And so that means put 2 into the function, the derivative, and the second derivative. Now, I want you to note that everything we do is all about that original function. So I'm going to go through it with a couple things. I'm going to pull out the old pink highlighter. I think I got the highlight. Here we go. So if we can get that going on here. We'll do a nice yellow highlighter and a pink pen. You want to know that everything we do is really about the original function f of x. So it's always about f. So when I find a derivative, it's telling me something about f of x. It's telling me the slope of the tangent on f of x. F double prime is telling me where it's concave up or concave down. And when I say it, I mean f of x. I want the original function. So the first and second derivative are just telling us stuff about this original function f of x, and it shouldn't ever tell you about anything else. And so always come back to the original function. Always have a graph of the original function sitting around. And there it is, by the way. I have it down at the bottom. It's got a lot of stuff on it right now, but this is a graph of f of x that I'm giving you, and I will give you on your quiz as well. And so back up to the original. If you get the derivative, first derivative, and the second derivative, and put 2 into all of them, you get out the appropriate values that you see here. And so if I look here in the original function, I get negative 68. What does that mean? Well, that's a coordinate point. That means if I go to 2 on the original function, it takes me to negative 68. It's the point 2, negative 68. It's the height at x equals 2. So old-fashioned, regular old algebra stuff there. But when you put it in the derivative, you get out 36. And what that tells you is that the slope of the tangent line to f of x, it's all about f of x, is 36 units per, and then, by the way, that's y units per 1 unit of x. So let's say this function was about dollars per year, then that would be $36 per year if my y was dollars and my x was in years. Okay, so you down below f double prime, 84, the number I get from plug it in there, it's positive. That's all we really care about. It means that this is at that particular x location, this is concave up. Let's go look at this. At x equals 2, I want you guys to look at this right here. This graph is totally concave up. Along x equals 2, everywhere in there, that graph is cupping in the upward direction. Okay, so that's what that stands for. When it's positive, concave up. When it's negative, that is f double prime, then it's concave down. The only things to talk about is the big deal is f prime of x and f double prime of x tell us about what's going on in f of x. It's all about f of x, and that's why we have a graph of it down below. Okay, part C. 2 things. I'm losing my voice. It's late at night, and my kids are in bed, so I want to be kind of quiet. But part C says find critical values, relative max and min, in intervals of increase and decrease. Well, critical values are really the peaks and the valleys. That's kind of what we're talking about. So if I go to my graph, I'm looking for peaks and valleys. But what you do to get it is you set f double prime of x, or f prime of x equal to 0. And in this particular case, that means this quadratic equal to 0 because that's our f prime of x. The only way you're going to solve this, I mean, the thing that always works is the quadratic formula. Negative b plus or minus b squared minus 4ac all over 2a. That's the quadratic formula. Use your calculator to evaluate that. I should do a little addition and multiplication there, and I got these values, and then I go ahead and plug it in my calculator. I get negative 2.189 and 1.523. If you look at your graph here, those are the x locations of the peak and the valley, respectively. If I want to find out what the coordinate point is of those, I just have to plug it back into f of x, because remember, these are x values on f of x. So I plug it back into f of x, and I get out 77 for the negative 2.189 x value, and I get out negative 76.267 for the 1.523 x value. So critical values are just setting the first derivative equal to 0 to tell me where that location of the peak in the value. Remember, your finger can point at that for me. It's not like you can't go in there and say, yeah, it's about -2 point something. Well, that's great. That's something you should know how to do, is to identify it in general. That value over there, yeah, it's about 1 point something something. That's all good, but what happens is somebody's going to ask you someday, yeah, that's great that you can point to it with your finger, but what exactly is the location of that peak and valley? And that's what setting the first derivative equal to 0 does, is it gives us the exact x location of that peak or valley. So that's why we use the first derivative, set it equal to 0. Gives us peaks and valleys. It's awesome. Now, in between a peak and a valley, the graph is going uphill or downhill. And I kind of color-coded it down here. Green is uphill, pink is downhill. And over here in interval notation is increasing from -infinity to the peak at -2.189, and also from the valley onto infinity, it's also uphill. Those are those two green regions you see in the graph below. It's decreasing in between the two peaks and valleys, so -2.189 to 1.53. So interval notation says from the following x value, these are x values, remember, this is all about x. Interval notation is all about x. They're just giving you the lower bound and the upper bound of x. So I might put lower bound x and upper bound x. And over here is lower bound x and upper bound x. That's what an interval is all about. It's telling you what's the low, the high for of the x value that indicates this, behavior, increasing or decreasing. Now, on the side here it says color is matching. So look at the color coding. If that helps, I hope it does. Go with that. Now down below, D is find the points of inflection. Well, to find the points of inflection, you have to set the second derivative equal to 0. And so we've got a second derivative. I did my work down below because I ran out of room. But here's my second derivative, set equal to 0. It's a linear equation. So I subtracted 12 from both sides, and I divide by 36, and I get -12 over 36, which is 1/3. So I kind of jumped to that conclusion, but I was assuming you could make that calculation. Well, x equals -1/3 is basically saying anywhere where x equals -1/3. But to get the actual point of inflection, that the x equals -1/3 is just the x coordinate. To get the point of inflection, you have to plug that -1/3 back into your original function. It's all about that original function. So when I put -1/3 into f of x, remember, not the derivative, not the second derivative, I put in the original, I got out 0.44, and it goes on repeating. So that's what you're seeing right here. The second derivative equal to 0, we got an x coordinate right here, -1/3. To get the y coordinate, I had to plug that into f of x. So -1/3 into f of x. Boom, that's how I got my 0.44. Okay, and remember that's what we have here. This is a graph of f of x. So if I want to find out what the location is vertically as an output, I have to put -1/3 into f of x to find out where I am along this curve along here. So those are all points. Okay, so there you have it. What we're talking about, remember, the first derivative is about slope of a tangent line. It's really nice to know when the slope of the tangent is 0 because it means a peak or a valley. We like that. The second derivative is about whether it's concave down or concave up. And the change in concavity happens when f double prime, the second derivative, is equal to 0. So it's the point where it changes from concave down to concave up or vice versa. Okay, those are big indicator points. Now we go back to the second page when we're talking about maximum revenue, etc. This one says a commodity has a demand function given here. Now in class, what we'd done with these demand functions, we had some data and we fit a model to it and got our demand curve. We did quadratic, cubics. I don't think we did a linear equation. I wish we did. I'm sure you wish we did because it is kind of simpler. But ultimately, all that matters is what you do is you take that demand function, which by the way could be called a price demand function. It's all about, for a given x value, it gives you the price. So you can think of, I literally dropped this price function here, right over here, and multiplied it by my number of units. Price times number of units tells you the money that's coming in. You know, if I set the price, if the market indicates the price should be $10, and I sell 50 units, that's a revenue of $500 because you multiply 10 times 50. Okay, so that's what we do. We're multiplying number of units times price. When it's a function like that, this is just a dynamic function that says, you know, I can tell you the price for whatever number of units is being produced on the market, and it's an equation. It's variable. It depends on how many products are out on the market. That's where price is a variable type of thing. We're always changing prices. If you guys notice about gas stations, they're the worst. You know, they're always changing their price, and it's a product of somebody sitting back there saying, hey, what's demand? What are people willing to pay? And so they modulate that price all the time. And when they modulate the price, the amount of gas people purchase changes with it. So you get the idea that this is a kind of a dynamic situation. So that's what we're doing here is we're doing for a particular situation. We have a price that was given to us, or an equation that gives us price for units times the number of units, and that gives us revenue. And that's something you just want to memorize too. Revenue is always X times P, and P is your demand function, your price demand function. Okay, so next thing, let's go ahead and simplify what we have. 90x minus 0.2x squared. If I graph it, it kind of has the look of this thing over here on the right-hand side. So this is my revenue function kind of graphed. What I want to know is where the peak of that occurs. And that didn't work out very well. The peak of my revenue curve, one of the things we remember is that if you set the derivative equal to 0, it's going to indicate where a peak or a valley will occur. And if you guys graph this revenue curve, you're going to realize, well, there's only one place where I have a horizontal tangent where the slope of the derivative of the tangent line is 0. That means where my first derivative is equal to 0. It's at this peak. There is no valley. So what's cool is I'm going to solve this. I'm going to set the derivative equal to 0 to find this location. R prime set equal to 0 is going to help me find the x that indicates that peak right there. And so I've done that right here. R prime of x is the derivative of, so here's my R of x is up here in a box, that pink box right there. R prime of x right here. Set it equal to 0, solve it, and you guys can follow the algebra, I'm sure of it, but I get 225 units. So what that means is that peak occurs at an x of 225. And if you want to know what the actual revenue is, because I do, I want to know how much money that is, you have to plug that back in. So you have to, if you want to know how much revenue you're taking in, then you got to go to the original revenue function. It's all about the original revenue function. Sorry, put a number in there. You put 225 in there, and you see what you get. Okay. Now I happen to have a graph of these things, and so I'm going to hit escape here. Let me show you my graph real fast. Here's my revenue function, and by the way, I've got it. If you look at it, my revenue maxes out at $10,125, and so that's pretty slick. And so that's the value I get for this, 10,125 bucks. Boom, boom, boom. But when it asks you for what price gives you the maximum, oops, I gotta erase something that's on here, by the way. There we go. Fix that little dude. So revenue is 10,125 from plugging into the revenue function. So imagine putting 225 right there and 225 right there into my revenue function. You can check my work, but it should give you 10,125 bucks. The price that you get that goes with that, that's a little bit different. It's 90 minus, I'm going to put it down here, and you guys can follow on my calculator here. The price, if I put 200 and, oops, P equals, well, let's put it in just straight up, 90 minus, and I'm not sure you guys are seeing what I'm showing on here. I'm trying to find my screen. Let me give you guys both options here. What I'm looking at is, let me show you what I put in there. I put 225 into my revenue function in for X, and so I'm showing that right here. That's where that go in there, and I get out $10,125. That's what happens. And here's the graph that goes with it, just to make sure you know where I'm getting that from. Bingo, here it is. That's the peak right there. Okay, maximum revenue. Now the price, that's by the way, that's an X of 225 and a revenue in dollars of $10,125.